All right, welcome back to the final lecture of the course 3.10. We're just going to give a summary of this third unit of material. And if you've made it this far and you're still watching the lectures, then I think that deserves a huge congratulations. You've made it. We're almost there. Let's just summarize what we have talked about in Unit 3. Now, it's we've covered it may seem like we've covered a lot of ground, a lot more than we did in the first two units, because we have roughly the same number of sections in this unit as we did in the first two units, but the sections were a lot longer. That said, I think that the reason the sections were longer, the reason the lectures were longer, is because it just takes a lot of time to kind of run the hypothesis tests and to really think through the problems more so than it did in the previous units. And so, really, when you boil it down, we really only talked about two main topics in this unit, and that was hypothesis testing and confidence intervals. So, what I would like to do in this summary is just kind of review a little bit about the logic behind hypothesis testing, review the logic behind confidence intervals. Along the way, we will discuss type 1 and type 2 errors, which have kind of been sort of like at the periphery of a lot of the things that we've talked about, but we haven't ever formally sort of defined those. And so now that we've seen several examples of hypothesis tests, I think it's a good time for us to kind of delve into those type 1 and type 2 errors a little bit more. And then finally, to kind of wrap up the section, I'd like to just kind of practice setting up the correct hypothesis test to run, and just kind of do a little bit of mixed practice, trying to incorporate kind of all of the hypothesis tests that we've talked about. So let's get started reviewing the logic behind hypothesis testing. So as we've discussed when we first introduced this topic, hypothesis testing is how we judge whether evidence that we've collected is mathematically compelling, or evidence that a researcher has collected is mathematically compelling. And we use it to decide whether the data that have been collected are adequately explained by the null hypothesis, or if the data indicate that the null hypothesis should be rejected. So the null hypothesis, H null, is the status quo, right? It's what we assume to be true until we have evidence otherwise. And so it's a statement of no change, no difference, no effect, right? The alternative hypothesis, HA, is usually the statement that the researcher is trying to find evidence to support. And of course, it's going to indicate change, difference, and effect. So, for example, let's say that a drug company is trying to develop a new antibiotic, but the FDA will not approve it if it causes headaches in more than 2% of the population. This is an example we've used several times, I think. So what might be done by the researchers is they might run an experiment where they give 300 people the new antibiotic, and let's say that 2.3% of those in their study experience a headache after taking the medication. Now, that's more than 2%. But the question is it possible that increased proportion is just due to random chance and really the antibiotic is safe to take? Or is possibly the antibiotic causing more headaches than the FDA can allow? Is there sufficient evidence to say that the new antibiotic should be discarded? Or is the increase, more likely to be explained by random chance? So this is where hypothesis testing comes in. And what the researchers would do is they would run a hypothesis test, right? They would run this test right here, testing to see if the true population proportion of people who take this medication and experience side effects is 2%, or if maybe it's more than that, right? So when we go to test a hypothesis like that one, we're going to follow the same 5 steps every time. Step 1 is to state the null and alternative hypotheses. Step 2 is to then gather the sample evidence, okay? And then step 3 is to compute the p-value. The p-value is the probability that we would obtain the sample evidence that we obtained in step 2 if, in fact, the null hypothesis were true. If that p-value is really small, then it tells us that we're probably wrong to make this assumption, and so we reject it, right? So that's step 4, is decide whether to reject or not reject the null hypothesis. A small p-value means that we should reject the null. How small exactly? Well, less than alpha, right? If the p-value is less than alpha, then we reject the null hypothesis. And then finally, what we would do is write a conclusion explaining what our decision means for the alternative, okay? So the decision is about the null. The conclusion is about the alternative. Let's just talk about the p-value a little bit, right? So as we said a second ago, the p-value is the probability of obtaining our sample evidence if the null hypothesis is assumed to be true. If the p-value is small, then it's really highly unlikely that we would have obtained the evidence that we obtained if we assume that the null hypothesis is true. And so we reject that assumption. You may wonder, and I've had students ask this in the past, but why wouldn't you reject the results? Like if you got a small p-value, yeah, it could be that the null hypothesis is true, but it could also be that there's some flaw in the study. And that's totally true, okay? But as a statistician, that's not really our job, right? As a statistician, it's our job to take the data that as it is and determine what we can conclude from it mathematically. And when we go to compute the p-value, mathematically what's happening is that we're not assuming anything about the data, right? The data are not assumed, they're observed. They are the reality. And so we can't reject those, okay? Mathematically speaking, the only assumption we make is that the null hypothesis is true. Okay, and so if we get a small p-value, that's the assumption that we have to reject, right? We have to reject the assumption that the null hypothesis is true. But yes, like if you're asking yourself this question, like I think that you're thinking good things and I'm proud of you, right? And I think that in the real world, like if you're trying to make sense of things in the real world, you should absolutely scrutinize a study's methodology to determine if the data are even valid in the first place, okay? But as a statistician, mathematically, the only assumption that we're making is that the null hypothesis is true. And so if we get a small p-value, that's an indication that we should reject that assumption. So let's practice interpreting some p-values here. Number 1 says, what's the meaning of the p-value? Give both a mathematical equation and explain it in words. Okay, so part A, suppose you want to test H null, p equals 0.41 against an alternative that p is less than 0.41. You collect a sample that has a sample proportion of p hat equals 0.38. Okay, so this sample proportion is our sample evidence in this case, and 0.38 is indeed less than 0.41. But the question is it enough of a difference, right? Is there enough of a difference between what we assumed in the null hypothesis and what we observed in our sample for us to conclude that the null hypothesis should be rejected? And to answer that question, we run a hypothesis test. And so let's say that we do that. Let's say that we run a hypothesis test and we get a p-value of 0.2143. We're asked to explain the meaning of this p-value. As always, you can pause this video, give it a try on your own, and then, resume playing and see what I say. I'm just going to kind of go through the examples and give you my responses to these. Okay, so if we get a p-value 0.2143, this is the probability of us obtaining this sample statistic if we assume that the null hypothesis is true. In math symbols, we might say this, okay? The p-value is the probability that we would obtain a sample proportion, p hat, of 0.38, or something more extreme than that, okay? And in this case, we're running a left-tailed test, so something more extreme than 0.38 would be something even less than 0.38, okay? So it's the probability of obtaining a sample proportion of 0.38 or less, assuming that, given that, the null hypothesis is true, right? Given that the population proportion is 0.41. Okay, that's the p-value. And we're told that that probability is 0.2143. So in words, we might say something like this. There's a 21.43% chance of obtaining a sample with a sample proportion of 0.38 or less, if in fact the population proportion is 0.41. Now, in this particular case, I think a 21.43% chance is not a low probability. That's actually a pretty likely outcome to occur. And so it does not cast any doubt whatsoever on our null hypothesis. We would say, oh yeah, this is well within the realm of possibility if we assume that the null hypothesis is true. And so there's just no reason to reject our null hypothesis. Our sample evidence seems to be gelling just fine with our assumption, okay? So we don't reject the null. Part B says, suppose you want to test H null mu equals 75 against an alternative that mu is greater than 75. You collect a sample that has a sample mean of 78. Okay, again, this sample mean is more than 75, right? But the question is it enough of a difference from what we're assuming in the null hypothesis for us to be doubtful of the null hypothesis? So we run a hypothesis test to determine whether or not that's the case. And in this time, it says we get a p-value of 0.0143, and we're asked to interpret that. So what I would say is this is the probability of us obtaining what we obtained in our sample if the null hypothesis were true. So if we assume that the true population mean is 75, then there's a 1.43% chance of us obtaining a sample mean of 78, or something more extreme than that. In math symbols, it would be this, okay? The p-value is the probability of getting a sample mean of 78, or something more extreme. In this case, we're running a right-tailed test, so something more extreme than 78 would be something even bigger than 78. So it's the probability of obtaining a sample mean of 78 or more if we assume that the true population mean is 75. We're told that there's just a little over a 1% chance of this occurring, right? 0.0143. Okay, so now you could phrase this exactly the same way that you phrased part A. You could say there's a 1.43% chance of obtaining a sample with a sample mean of 78 if, in fact, the true population mean is 75. I'm just going to rearrange those terms a little bit just to kind of, give the interpretation a little different flavor in case it kind of makes more sense to you if I state it in a different way. So if I state it differently, something that I might say is, well, if we assume that the true population mean is 75, right? If we assume that the true population mean is mu equals 75, then there's a 1.43% chance of obtaining a sample with a sample mean of x bar equals 78 or more. Okay, so that's how we would say it in words. Now in this case, I would say a 1.43% chance, that is a pretty slim chance. That would make us kind of doubt whether or not the null hypothesis is true. And so we would reject our assumption, right? We would say, it's highly unlikely that we would observe what we observed if we assume the null hypothesis is true, and so we should reject the null hypothesis. Okay, so that's a little review of the p-value. Now, The question, and we've already answered this, but I want to delve into this a little more deeply, right? Exactly how small should the p-value be to reject the null hypothesis? And the answer that we've given is it should be smaller than the level of significance, right? It should be smaller than alpha. I want to talk a little bit more about what alpha is in this section now that we've seen some more examples, okay? Alpha is the probability of committing what's called a type 1 error. And we're going to talk about that in the next little subsection here. But alpha is chosen by the researcher before the data are collected. For now, just recall that alpha is related to our level of confidence, right? Our level of significance is related to our level of confidence. In particular, they are complements of one another, okay? So if our confidence level is 95%, then our significance level is 5%. We typically will give a significance level as a decimal and a confidence level as a percentage, but clearly they're still complements of each other, right? What this means, the way that we would interpret this is, if we want to be 95% confident that we are not rejecting a true null hypothesis, then our p-value needs to be less than 0.05. If we want to be 99% confident, then our p-value needs to be less than 0.01. And in general, if we want to be this confident, then our p-value needs to be less than alpha, okay? We'll talk a little bit more about type 1 and type 2 errors, and then you'll get a better sense for what alpha is in the next little subsection. Now, a couple more things to say about hypothesis testing and just kind of the logic of it, okay? Note that our decision is always either to reject the null hypothesis or to not reject the null hypothesis. Those are the only two options on the table. We never accept the null hypothesis. And I've seen this creeping into some of your problem sets that you've turned in and stuff, and so you need to avoid that language. We do not accept the null hypothesis. That is not an option on the table. Deciding not to reject the null hypothesis is not the same thing as accepting the null hypothesis. I know it seems like it's similar. Well, it is similar, right? It's similar, but it seems like it's the same. It seems like it should be considered to be the same thing, but it's not, okay? It's similar to how a not guilty verdict is not the same thing as declaring someone innocent, right? Sometimes there's just simply not sufficient evidence to convict the defendant in a criminal trial, right? And so it may be that they're guilty, but you just don't have enough evidence to convict them. And it's the same way with hypothesis testing, okay? So we're not accepting the null hypothesis whenever we fail to reject it. It's just that we don't have sufficient evidence to reject it. And so that's what we say. That's why we word our conclusions the way that we do. And then finally, one last thing to note, in our decisions and our conclusions, all of the negations go together, right? All of the nots in our statements go together. There's never any mixing and matching in hypothesis testing. If our p-value is less than alpha, then we reject the null. And there is sufficient evidence to support the alternative, right? So if our p-value is less than alpha, then we decide to reject the null and we conclude that there is sufficient evidence, okay? If our p-value is not less than alpha, then we do not reject the null and then we conclude that there is not sufficient evidence to support the alternative. Please, please do not lose points on test 3 by mixing and matching here. It is never appropriate to do that. There should be no mixing and matching. Okay, so there's a plane outside my window. You might be able to hear it. Anyway, let's talk about type 1 and type 2 errors a little bit more. Actually, let's just introduce them because we haven't really introduced them yet. So let's talk about these. Because the decision in a hypothesis test is based on incomplete information, right? It's based on sample information. And consequently, we can never be 100% certain that we're making the correct decision. We don't know whether we're making the correct decision or not. We can try to minimize the probability that we make a wrong decision, but ultimately we'll never know if we're making the right decision. In fact, there are 4 possible outcomes in a hypothesis test. So these first 2 outcomes are correct decisions, okay? If we reject the null hypothesis when the alternative hypothesis is true, then that's a good thing, right? Because if the alternative hypothesis is true, then we want to reject the null. So that would be a correct decision. We sometimes call that a true positive, okay? Another way we can make a correct decision would be to not reject the null hypothesis when the null hypothesis is true. This would also be a good thing, right? Because if the null hypothesis is true, then we don't want to reject it. So this is sometimes called a true negative. But then we have these other two possibilities, okay? If we reject the null hypothesis when in fact the null hypothesis is true, then we've made the wrong decision. And this is called a type 1 error, okay? Type 1 errors are sometimes called false positives. This would be like if you know for a fact that you do not have COVID and you take a COVID test and it comes back positive, right? If somehow you knew going into it that you didn't have, that illness, and the test comes back positive, then you've got a false positive. That's a type 1 error, okay? And then finally, the fourth possibility is we decide not to reject the null hypothesis when the alternative hypothesis is true. And that would once again be an incorrect decision, because if the alternative hypothesis is true, then we should reject the null hypothesis. If we fail to do that, then we've made a mistake, right? We've committed what's called a type 2 error. And type 2 errors are sometimes called false negatives. This would be like if you know that you do have COVID, but you take a COVID test and it comes back negative, right? So here's a little chart for those of you who think more visually. We have some kind of reality, right? Some kind of reality that we're trying to figure out, but we don't really know, okay? And then, but what we're doing is we're running a hypothesis test to try to figure out what the most likely reality is, okay? And then we have our conclusion. We have the conclusion of our hypothesis test. If the conclusion of our hypothesis test matches reality, then we've made a correct decision, right? And that could happen if, for example, the null hypothesis is true and we don't reject it. It could also happen if the alternative hypothesis is true and we reject the null. Those would both be correct decisions. When our conclusion does not match reality, then we've committed a type 1 error or a type 2 error, okay? If we reject a true null hypothesis, then we've committed a type 1 error. If we fail to reject a false null hypothesis, then we've committed a type 2 error, okay? And again, this is sometimes confusing for students, but it's like we don't know when we're committing an error in a hypothesis test, but we do have to account for the fact that it's possible we might be committing an error. And that's exactly what our level of significance is, okay? More on that in a second. Okay, so I've already talked about these examples about false negatives, false positives. Another way to think about it is, again, in terms of a criminal trial, right? A type 1 error would be like convicting an innocent defendant, which I think we can agree would be a horrible thing to do. You don't want to put an innocent person behind bars or fine them or whatever. A type 2 error, on the other hand, would be like acquitting a guilty defendant, which is also bad, right? If you have somebody who's a danger to society, you don't necessarily want them roaming the streets free. You would like to convict guilty people. But it happens, right? It happens. Sometimes you don't have enough evidence to convict somebody who's guilty, and so you end up acquitting them. So that's a type 2 error. Let's practice describing what a type 1 and a type 2 error would be. Number 2 here says, a drug company is trying to develop a new antibiotic, but the FDA will not approve it if it causes headaches in more than 2% of the population. So same kind of scenario that we talked about earlier on in the notes. It says the researchers run the appropriate hypothesis test to determine if their drug causes headaches in more than 2% of the population. And that would be this test. Okay. We're asked to explain what it would mean to make a type 1 error and what it would mean to make a type 2 error. So a type 1 error is rejecting a true null hypothesis. It would be, in this case, rejecting the idea that only 2% of people experience headaches, when in fact that is true, right? It would be, maybe a better way to say it would be concluding that more than 2% of people experience headaches, when in fact only 2% of them do, right? That would be a type 1 error in this case. So let's write that down. This would happen if we conclude that more than 2% of people who take this antibiotic experience headaches. When, in fact, only 2% of them do. You could even say 2% or less, right? Okay, so that's a type 1 error. A type 2 error is very similar, but it's kind of in reverse, right? A type 2 error is when we fail to reject the null hypothesis even though it's false, okay? In this case, it would be like concluding that only 2% of people experience headaches as a side effect when in fact more than 2% of them do, okay? So I'm just going to take my previous interpretation and just kind of adjust it here by swapping some things around, right? This would happen if we conclude that only 2% of people who take this antibiotic experience headaches. When, in fact, only 2% of them do. Okay, so that's type 1 and type 2 errors. Now, as previously stated, the probability of making a type 1 error is called the level of significance alpha. Alpha is chosen by the researcher based on the severity of the consequences of making a type 1 error, because alpha is the probability of doing just that, right? It's the probability of making a type 1 error. It's chosen, and all of the other parameters of the test are built based on that choice, okay? So in criminal trials, for example, we don't want to convict a lot of innocent defendants, and so alpha should be small. And it's the same with hypothesis testing. We don't want to reject a bunch of true null hypotheses, and so we want alpha to be a small number, right? We want the threshold for rejecting the null hypothesis to be pretty small, which kind of begs the question, why don't we always just make it really small? Like, why don't we make it 0.01 every time? And the answer to that is reducing the probability of making a type 1 error increases the probability of making a type 2 error. They're not exactly complements of one another, and both probabilities, the probability of making a type 1 or a type 2 error, can both be reduced with larger sample sizes, okay? But there's a negative relationship between these two types of errors, right? If you decrease the probability of committing one, you're going to increase the probability of committing the other, unless you're doing something like increasing your sample size, okay? So in the real world, the way that we see something like this is, to ensure that innocent defendants are not convicted, juries are instructed to convict only if the evidence against the defendant leaves no room for reasonable doubt. And consequently, a lot of guilty defendants are going to be acquitted, right? And so you can see how type 1 and type 2 errors, there's going to be kind of a balancing act when you're trying to choose your level of significance. So for our class, we don't really have to worry about that too much because that's something that the researcher chooses. So we're not going to have to choose a level of significance when we're running any hypothesis tests. But as we've seen, the most commonly used values are these three. And of those three, 0.05 is like almost always the one that's used. Okay. So we've reviewed the logic behind hypothesis testing. We've talked about type 1 and type 2 errors and how they relate to the level of significance and all of that. Let's talk about the logic behind confidence intervals, okay? Because hypothesis tests, when we're performing inference, hypothesis tests really only tell us half the story. They help us determine if the results in our sample are indicative of some kind of deviation from the null hypothesis at the population level, but they don't indicate anything about the magnitude of that deviation. Confidence intervals are used to get an estimate for how far a population differs from the assumption in the null hypothesis. So hypothesis tests tell us about statistical significance. They answer the question, is there a difference? Okay. Whereas confidence intervals tell us about practical significance. They tell us how big is the difference. Okay. So once you've rejected the null hypothesis in a hypothesis test, then you know that there's a difference. Okay. But then the question is, how big is the effect? How big is the difference? Now, because our estimates are based on incomplete sample information, we are 0% sure that our parameter that we're trying to estimate is equal to the sample statistic that we're using to estimate it. If we want to have any level of confidence in our estimate, we have to give a range of values that the parameter could equal. And so that's why confidence intervals are intervals of numbers. We're not just going to give point estimates where we say, mu equals 75. We're going to give a range. We're going to say mu is somewhere between 74 and 76, right? And we can put an exact number to how confident we are that a given parameter falls within a certain range. So let's just practice interpreting a few confidence intervals. Number 3 here asks us to do that. Part A says, a 95% confidence interval for the proportion of drunk drivers on the road between 1 and 2 p.m. is 0.034 and 0.042. That's kind of a scary thought, but you should take it with a grain of salt. Let's give our interpretation, right? Again, feel free to pause the video, try this out. Here's my interpretation, though. I'd say, well, we're 95% sure that the true population proportion of drunk drivers between 1 and 2 p.m. is somewhere between 0.034 and 0.042. Okay, so that's a good interpretation of that confidence interval. Now you could state this differently, right? You could say somewhere we're 95% sure that somewhere between 3.4% and 4.2% of drivers on the road from 1 to 2 p.m. are drunk. Okay, so that's another way that you could interpret it. Both of those interpretations are totally good. Okay. So that's how we would interpret a confidence interval for a proportion. Part B asks us to interpret a confidence interval for a mean. It says a 90% confidence interval for the mean age in years of drunk drivers on the road between 1 and 2 p.m. is 21.3 to 24.2. Okay, so again, there are different ways that you could word this interpretation. I'm not going to give you multiple ways on all of these. I'll just give you one. But I would say something like, well, we're 90% sure that the true population mean age of drunk drivers between 1 and 2 p.m. is somewhere between 21.3, and 24.2 years old. Or you could say we're 90% sure that the average drunk driver between 1 and 2 p.m. is somewhere between 21.3 and 24.2 years old, right? Something like that. These estimates, of course, are based on some kind of sample evidence. Like in part B, the way that the researchers obtained this interval is by first collecting some sample and then computing a sample mean. And that sample mean would have sat right in the middle of that interval. So, X bar would have been, I don't know what number is right in between 21.3 and 24.2. I'm guessing it's like 20, well, it's 21.75 or something like that. Anyway, but, they might come up with that sample mean. We're 0% sure that the population mean would be 21.7 though, right? It's like the researchers got this sample mean. They're 100% sure that in their sample of however many drivers they had in their sample, they're 100% sure that the sample mean is 21.7, 0% sure that the population mean is 21.7. But we are 90% sure that the population mean is somewhere between 21.3 and 24.2, right? So this is the idea behind confidence intervals. Let's look at a couple more. Let's look at some two-sample confidence intervals. You've struggled with these a little bit on the weekly problem sets, so let's make sure that we've got this down. So part C. A recent survey found that 67% of U.S. women and 65% of U.S. men plan to vote in the next presidential election. A 99% confidence interval for the difference in the proportion of women and men who plan to vote is 0.011 and 0.029. Some of the misinterpretations that I've seen about confidence intervals is that, some of you have thought that the lower bound is an estimate for the percentage of women, and the upper bound is an estimate for the percentage of men, but that is not true. This is a confidence interval for the difference in the proportions. In other words, if you took the difference, if you subtracted the proportion of women and men who plan to vote, what would the difference in the proportions be? And we're estimating it to be somewhere between 1.1% and 2.9%, right? That's what this interval means. We would say something like, and that makes sense given the sample data, right? In the sample, there was a 2% difference, right? There was a 2% difference. Do you see that? So there was a 2% difference in the sample. So in the population, we would expect there to be somewhere between a 1.1% and a 2.9% difference. All right. So we are 99% sure that there will be somewhere between, and there's my dog snoring in the background. You can't get through one of these lectures without my dog snoring in the background. And it doesn't matter when I record these. If I'm recording at 11 a.m., if I'm recording at 5:38 p.m. like I am right now, he's going to be snoring. Okay. Anyway, we're 99% sure that there will be somewhere between a 1.1% and 2.9% difference in the proportion of women and men who vote in the next presidential election. Okay. So that's that one. Now, part D, one more of these. So part D says, a recent survey found that the mean height of registered Democrats is 55.2 inches and the mean height of registered Republicans is 57.4 inches. So Republicans are a little taller, right? You can probably think of reasons that this might be true. So we're told a 95% confidence interval for the difference in the mean height in inches of Democrats and Republicans is negative 2.8 to negative 1.6. Now, here, this is a confidence interval for the difference in the means, right? Again, it's not the case that the estimate for the average height of Democrats is negative 2.8 inches. That doesn't make any sense at all. And that the mean height of Republicans is negative 1.6 inches. It's just not even close to being correct. This is a difference. And the reason we're getting negative answers is because Democrats are shorter than Republicans. So when you do 55.2 minus 57.4, then you get something like, what would that be? So negative 2.2, right? You get negative 2.2. Okay. So in our sample, there was a difference in the means of 2.2 inches, with Democrats being shorter than Republicans. And so at the population level, we would expect there to be a difference somewhere between negative 2.8 and negative 1.6 inches. Or rather, a difference of 2.8, somewhere between 2.8 and 1.6 inches, with Democrats being shorter than Republicans. Okay, so I might say something like this in my interpretation. This was a 95% confidence interval, right? So I would say we are 95% sure that, well, you could say it a bunch of ways. Maybe this would be a good way to say it. We're 95% sure that Democrats are somewhere between 1.6 and 2.8 inches shorter than Republicans on average. Or you could say, we're 95% sure that the difference in the mean height of Democrats and Republicans is somewhere between negative 2.8 and negative 1.6 inches, right? So you could say something like that. But this is the meaning of these intervals. Okay. Again, these intervals give us some sense for the magnitude of the differences that we're seeing. Okay. So they tell us, how much practical difference there is in our results. Okay. So what I want to do for the remainder of this section is to just go over the different hypothesis tests that we've discussed. For any of the 1 or 2 sample hypothesis tests that we're going to review, there are corresponding confidence intervals to go along with them. And I'm not going to give you like full-blown examples of running hypothesis tests and answering follow-up questions and constructing confidence intervals, because that would make for a very, very long lecture. Hopefully, over the course of the last several weeks, as we've been talking about inferential statistics, you've increased your capacity to perform mathematical inference and to think through questions about inference. And so I'm not going to give you any examples of actually running any tests, but I do think that one thing you might struggle with and that you might want to practice is setting up the correct test in the first place, because we've covered 9 different hypothesis tests, and you might be a little bit fuzzy about when to apply which test. And so let's review. We talked about 4 tests for proportions. We talked about the one sample proportion test, and this is where you're just saying p equals some number, like p equals 0.35, and then you can run it two-tailed, left-tailed, or right-tailed, right? Those are your options. So that's the one sample proportion test. We talked about a 2 sample proportion test. And by the way, in parentheses, I'm giving you the app from Art of Stat that you can use to run these tests. I'll put a list of these apps into a document or maybe a page on Canvas so that you'll have them all in one place, and then you can just click the links to go directly to the app that you need. But for now, these are the apps that you would use, okay? So for the one sample proportion test, you use the inference for a proportion app. For a two sample proportion test, you use the compare two proportions app. With a two sample proportion test, of course, you're comparing proportions from two different samples. And these are the way that you would state the hypotheses. You would literally write P1 equals P2 as your null hypothesis. You wouldn't need to try to change the numbers or anything. The third test that we talked about for testing proportions is the goodness of fit. In ArtofStat, you would use what's called the chi-square test app, and then click on the goodness of fit option along the top menu. The goodness of fit test is a generalization of the one sample proportion test, in the sense that your null hypothesis will be that P1 equals some value and P2 equals some other value, and so forth. And all of these proportions in the goodness of fit are coming from a single sample. So it is a one sample test. It's just that you're testing multiple proportions from that sample, right? So that's the goodness of fit test. The homogeneity of proportions test, on the other hand, for that one, you will also use the chi-squared test app in ArtofStat, but you will, instead of running the goodness of fit test on it, you'll run the test for independence or homogeneity. Anyway, with this test, the null and alternative hypothesis, or the null hypothesis is that P1 equals P2 equals P3 and so forth. Notice that here we have a generalization of the two sample proportion test, because what we're doing with the homogeneity test is we're testing proportions from different samples, from k different samples. And we don't care what the proportions are equal to. We don't care what the numbers are. We just want to know if they're equal to each other, okay? And so this is literally how you would state the null hypothesis in a homogeneity test. So those were the four tests for proportions. Now, we also had four tests for means, okay? We have the one sample t-test for testing a mean from one sample, okay? And it's very similar to the one sample proportion test. You would use the inference for a mean app to run that test. We talked about the two sample t-test. For this one, you would use the compare two means app, and you would click on confidence interval and significance test. The two sample t-test is for comparing means from two different samples where the sampling is independent sampling, okay? The matched pairs t-test, on the other hand, you would also use the compare two means app, but you would click on two dependent samples, because if you're running a matched pairs t-test, it's because you have two matched pairs. You have two samples that are matched pairs. They are dependent samples. So just as kind of a reminder of that concept, independent samples are samples that have nothing to do with each other, in the sense that when you collected one of your samples, the way that you collected that sample didn't automatically determine what your second sample would be. Okay? If you have independent samples, then the sample sizes could be the same size, but they could also be different sizes because they're not matched up in any way. Okay? With a matched pairs sampling, dependent sampling, on the other hand, you do have matched pairs, right? And so the sample sizes would have to be equal because you need to have matched pairs. In matched pairs or dependent sampling, the way that you collect your first sample automatically determines what your second sample would be, because you have to get the matched pair for the individual in the first sample. An example of matched pair sampling would be like befores and afters. If you're looking at somebody's weight before taking some kind of weight loss supplement, and then 6 weeks after taking the weight loss supplement, then you have matched pairs. Each individual is a matched pair with him or herself. So befores and afters are matched pairs. Husband and wife, like if you're comparing wives, the IQs of wives to the IQs of their husbands, then you would have matched pairs, right? Each wife is a matched pair with her husband. Siblings, right? Things like this. These would be matched pairs samples. And so we have those two tests for comparing two means. And then finally, if you're comparing more than two means, then you would use the one-way ANOVA. Okay? And this is kind of just an extension of the two-sample t-test, okay? Only you would have multiple means that you're trying to compare to each other. So those are 8 of the hypothesis tests that we've introduced. The last hypothesis test that we introduced was the linear correlation test. And in many ways, this is the easiest one to identify because you would have to be told pretty point blank in the problem to run a linear correlation test, right? With a linear correlation test in Art of Stat, you're going to use the linear regression app to run the test. The null hypothesis is that the population correlation coefficient rho is equal to 0, which would indicate that there is a I got these backwards. I'll fix this. I'll fix this so yours should be correct. But the null hypothesis is that there is not a linear correlation. And the alternative hypothesis is that there is a linear correlation, right? So the null hypothesis is that rho equals 0. The alternative is that rho does not equal 0. You could run a linear correlation test left-tailed or right-tailed, but the app that we use doesn't give us that option, so we're going to run it two-tailed every time. Okay, so that's kind of like a basic summary and review of all the hypothesis tests. Again, there were 9 of them in total. If you're confronted with some situation where you're asked to run a hypothesis test and you're trying to decide which test to run, then here are some guidelines for that. Okay, so to determine which test to run, the very first question you should ask yourself is, what parameter am I testing? And there are 2 options. You're either going to be testing a proportion or you're going to be testing a mean. Well, okay, there are 3 options, right? Because you could potentially be asked to run a linear correlation test, but that will be obvious, right? Linear correlation tests will be obvious because the problem will have to ask you to test whether there is a linear correlation, and so you'll know, all right? But for the proportion tests and the mean tests, right, you have to decide, okay, which parameter are they asking me for here? Are they asking for a proportion or a mean? Now, the problem might come out and just say it blatantly, right? The problem might say something about test whether the mean is so-and-so, right? Or test whether the proportion of people who have this characteristic are blah, 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 right? And so then it's really clear, right? If the problem says something about means or averages, then you're most likely going to be testing means. If the problem says something about proportions or percentages, then you're most likely going to be testing proportions. Now, if the problem doesn't use any of those keywords, then I find a really good kind of way to decide what parameter you're testing is to try to imagine what kind of variable you are testing. Try to imagine what the raw data would look like, okay? To help you answer what kind of variable you're testing. Because if you're testing a categorical variable, then the values would not be numbers, right? And so you would not be able to test means. You wouldn't be able to calculate the mean of a categorical variable. You would most likely be testing proportions in that case, okay? So if you've got a categorical variable, then you're testing proportions. If you've got a numerical variable, then you're testing means, okay? So this is the first step, right? The first step is to decide what parameter am I testing? Am I testing a proportion or am I testing a mean? Or are they asking me for a linear correlation test, right? Now, once you know what parameter you're testing, you should ask yourself how many parameters you're testing, okay? So let's say that you've decided I'm testing proportions. You should then ask yourself, how many proportions am I testing? And if you're only testing 1, then you run a 1-sample proportion test. If you're testing 2 proportions, then you run a 2-sample proportion test, right? Pretty straightforward. If you're testing more than 2 proportions, this is where it may get a little bit tricky. What you should do is ask yourself whether you have exact values for each proportion in the null hypothesis. If you do, then you should be running a goodness of fit. Okay? If you don't, then you should be running a homogeneity test. So that's how you decide what test to run if you know that you're running proportions. If you know that you're testing means, then again, you should ask yourself, okay, how many means? How many means am I testing here? If it's 1 mean, well, then you should run a 1-sample t-test. If you're testing 2 means, then you have to ask yourself a follow-up question, right? You have to ask, okay, are these samples independent or dependent? Okay? If they're independent, then you should run a 2-sample t-test. And if they're dependent, then you run a matched pairs t-test. okay? And we've already reviewed the difference between independent and dependent sampling. Finally, if you're testing more than two means, then you should run an ANOVA. Now, we did spend a lot of time in sections 3.6 through 3.9 reframing some of these tests in terms of independence. So instead of stating the hypotheses the way that I've listed them here on this page, we practiced stating them in terms of independence, right? And kind of changed our perspective there. I'm not going to put any questions about independence on the test, though. So you're not going to be tested on any of that material from 3.6 to 3.9. You will be required to demonstrate your understanding of that material by completing the dataset analysis project. But for the test, I just want you to state the hypotheses the way that we did on the previous page, on page 6 of this set of notes. And not worry too much about independence for the test. And by the way, any of the hypothesis tests that we've talked about, with exception to the one sample tests. So with exception to the one sample t-test and the one sample proportion test, the other 7 tests that we covered, they could all be stated in terms of independence. They could be rephrased in terms of independence. But again, you're not going to be asked to do that on the test. You'll be kind of tested on that by completing the dataset analysis project. So you can kind of, for this test, you can kind of breathe a little bit easy and not worry so much about the material in 3.6 through 3.9. Okay, with all of that in mind, let's, for the remainder of this section, I'm just going to take you through, I think I have like 9 or 10 examples, and what we'll do is we'll just practice setting up the hypotheses and figuring out what test to run, okay? So part A here says, in October 1945, the Gallup organization asked 1,487 randomly sampled Americans, do you think we can develop a way to protect ourselves from atomic bombs in case other countries tried to use them against us? 788 responded yes. Did a majority of Americans feel the United States could develop a way to protect itself from atomic bombs in 1945? And that should say develop. I'll try to remember to fix that in your notes. Okay, so if I'm trying to figure out what test to run, the first thing I should do is figure out, okay, am I testing means or am I testing proportions, or am I being asked for a linear correlation? And I think right off the bat we can rule out the linear correlation. It doesn't say anything about running a linear correlation test, so we can forget that. Am I testing means or am I testing proportions? Well, the problem doesn't say the word proportion. It doesn't say anything about percentages. But what it's describing is that we have some kind of characteristic we're interested in, right? Do people think we can develop a way to protect ourselves from atomic bombs? And we're counting up the number of successes, right? So we have a number of successes out of a certain number of individuals. And that screams proportion, right? That screams that, oh, I should take the 788 and divide it by the 1487 to figure out what proportion or what percentage of people answered yes to the question, okay? And so that just screams proportions. We should be testing proportions here. Another way to think about it is, if you think about what the raw data would look like, some researcher went out and asked people, do you think we can develop a way to protect ourselves from atomic bombs? And the responses that came in were not 14, right? The responses that came in were yes or no. Well, you can't compute the mean of a list of yeses and nos. What you can do is count up the number of yeses and figure out what percentage of the responses were yeses. So we're testing proportions, right? We've got to be testing proportions. So the next question then is, how many proportions are we testing? And I only see one sample being described, right? We only sampled one group of Americans, so we must be running a one sample proportion test. Our null hypothesis would be that P equals something, and our alternative hypothesis would be, well, we'll have to think about this, right? We're definitely testing proportions. The question is, did a majority of Americans feel they could develop a way to protect themselves from atomic bombs? Majority means more than 50%, okay? More than 50%. Now, the null hypothesis is always a statement of equality. It's a statement of no change, no difference, no effect. So the null hypothesis would be no, a majority did not feel this way. Only 50% felt this way, right? P equals 50%. And the alternative would be that P is greater than 50%, that more than half of people, a majority of people, felt that we could develop a way to protect ourselves from atomic bombs. Now, I'll be honest with you, that particular question is a tricky one. If you looked at that and you kind of struggled a little bit, that's understandable because that's kind of a tricky one. If you can do that one, then you're in good shape, okay? Because it really is not going to get any trickier than that. To run a one sample proportion test, we would, I forget the names of these stupid apps. We would, for a one sample proportion, run a inference for a proportion. We would go to the inference for a proportion app. One sample. Maybe I'll just name the test instead of writing down what app I'm using. But I'm just going to call it, it's a one sample proportion test. One sample proportion test. Okay, part B. Among individuals who had credit cards in 2010, the mean number of credit cards was 3.5, according to the Federal Reserve Bank of Boston. A random sample of 160 credit card holders has a mean of 3.3 cards and a standard deviation of 2.3 cards. Do these results imply that the mean number of cards per individual is now less than 3.5? Right? It was 3.5 in 2010, but this new sample has a mean of 3.3. Can we conclude that the mean is now less than 3.5? Clearly, we're testing means. I mean, the word mean was used, 3 times in this example. We're clearly testing means here, okay? The null hypothesis. Now, the question is, how many means are we testing? And again, I only see one sample being described. There was a mean that we're going to kind of assume to be the case until we have evidence to suggest otherwise, but we only had one sample that was collected to try to sort of disprove that mean. And so we should be running a one sample mean test or a one sample t-test. So we're just testing one mean. And the null hypothesis is that there's no difference between now and 2010. The mean number of credit cards is the same as it was in 2010, right? So mu equals 3.5. The alternative hypothesis is that mu is now less than that, right? Less than 3.5. This is the test that we're asked to run. And our evidence is that the sample mean was 3.3, right? That's our evidence. But that's not the test that we're running. We're going to use that to test our claim. But the claim is that the mean is less than 3.5. So this is a one sample t-test. Okay, part C. Kumon promotes a method of studying mathematics that it claims develops mathematical ability. In one question on an exam, a random sample of 350 non-Kumon students resulted in 73 getting the correct answer. For the same question, a random sample of 400 Kumon students resulted in 130 getting the correct answer. Are Kumon's claims substantiated? Okay, this is another tricky one because there's no mention of the word mean, there's no mention of the word proportion, there's no percentages going on here, no averages are talked about. So we have to decide. In this case, it looks like, once again, we're counting up the number of people who got the correct answer. Okay, so we're counting up the number of successes. We're given, I think we have two groups this time. We have a non-Kumon group, right? Students who didn't use the program, I guess. And then we have a Kumon group, right? Students who did use the program. We'll call that group 2. And it looks like we want to compare the percentage or the proportion of students who got the right answer in both of those groups, right? For group 1, it was 73 out of 350. And for group 2, it was 130 out of 400. So we're definitely testing proportions here. Again, you could think about what would the raw data look like here. What you would have is a list for the Kumon students that said, did you get the right answer? And the answer and the possible responses would be yes or no. Okay? And you'd be counting up the number of yeses. you'd have one column for the Kumon students and one for the non-Kumon students, but they would be yeses and nos, right? You'd be looking at categorical data, so you must be testing proportions here. We're testing two proportions because we're comparing two groups. So the null hypothesis is going to be that P1 equals P2. For the alternative, we want to know if Kumon's claims are substantiated. Well, what are Kumon's claims? They claim that their method improves mathematical ability. If that's true, then we would expect the Kumon students, which are group 2, to have a higher percentage of correct answers than the non-Kumon students, which are group 1. So we expect P2 to be bigger than P1, okay? Or in other words, P1 to be less than P2. So this is a 2-sample proportion test. Okay, here's another one. Part D. The following data represent the daily volume in millions of General Electric stock and Pfizer stock on the same 13 randomly selected days in 2010. Determine if the daily volume of GE stock is greater than that of Pfizer. Okay, so another tricky one, because no mention of the word mean, no mention of the word proportion. This time we're actually given the raw data. It looks like we have the data for GE, the daily volume of GE stock on 13 randomly selected days, and then the daily volume of Pfizer stock on the same 13 days, right? So we've got that raw data. We can clearly see that that data is numerical, which means we're most likely testing means. To further sort of verify that that is indeed what we should be testing here, let's think about this. We want to determine if the daily volume of GE stock is greater than that of Pfizer. Well, on some days it is, right? Like on this day. But on some days it isn't, like on this day. Okay? So what do we mean is the daily volume of GE stock greater than that of Pfizer? It is on some days and it isn't on others. So clearly what we mean is, typically speaking, or on average, right, is the daily volume of GE stock greater than that of Pfizer. So clearly we should be testing averages here, or means, okay? And it looks to me like we've got two groups, GE, we've got the GE stock, and we've got the Pfizer stock. So those are the two means that we're going to be comparing to each other. Since we're comparing two means, we do have to ask ourselves a follow-up question. Are these samples independent or dependent? And in this case, I would say that these are dependent samples, right? They are dependent samples because we're choosing the stock on the same 13 days. You could kind of think of it like this. Once I've chosen the GE stock, I automatically get the Pfizer stock because I have to choose their daily volumes on the same 13 days. Another way to see it is that, well, you've got matched pairs, right? This was the GE stock on a certain day, and this was the Pfizer stock on that same day, right? So we've got matched pairs samples here. Okay, so my null hypothesis is that the means are the same. mu1 equals mu2. We want to know if the daily volume of GE is greater. We call GE group 1, so we want to know if group 1 is greater than group 2. And we said that these were dependent samples, right? These are dependent samples. So I'm going to use a matched pairs t-test. Okay, part E. An engineer wanted to determine how the weight of a car affects gas mileage. The following data represents the weights of various domestic cars and their miles per gallon in the city. And we've got the data there. It says determine whether there is a linear correlation between weight and miles per gallon. And here it is, right? The dead giveaway. We're asked to determine if there's a linear correlation. So clearly we're going to be running a linear correlation test. Okay. So null hypothesis is that rho equals 0. And the alternative is that rho does not equal 0. Okay. Rho equals 0, no linear correlation. Rho not equal 0 means there is a linear correlation. And we would run this test by going to the linear regression app. We're going to run a linear correlation test. Okay, dead giveaway, right? Part F. In the Spacelab Life Sciences 2 payload, 14 male rats were sent to space. Upon their return, the red blood cell mass of the rats was determined. A control group of 14 male rats was held under the same conditions except for spaceflight as the space rats, and their red blood cell mass was also determined when the space rats returned. The project resulted in the data listed below. We've got a group of flight animals who went to outer space, and then we have a group of control animals who stayed on Earth. Okay, so we've got these two groups, group 1, group 2. Does the evidence suggest that the flight animals have a different red blood cell mass from the control animals? Once again, doesn't look like it's saying anything about means or proportions, but we have the raw data and it's clearly numerical. It's clearly numerical data here, so we're going to be testing means. Do the flight animals have a different red blood cell mass? Well, yes, some of them have different red blood cell masses. But the question is, on average, right? On average, do the flight animals have a different red blood cell mass from the control animals? The null hypothesis would be that they do not, right? That the groups have the same red blood cell mass. The alternative hypothesis, well, it looks like we're not being asked if one of the groups is bigger than the others. We just want to know if they're different, right? So the alternative would be that mu1 does not equal mu2. So now here we have two means. We're testing two means. We have to decide if the samples are independent or dependent to know which test to run. And in this case, even though our sample sizes are the same, both samples have 14 rats in them, but they are independent samples because the way that the flight rats were chosen had no bearing whatsoever on the way the control rats were chosen. They're not matched up in any way. This isn't like a before and after thing. They could have done a before and after. They could have measured the red blood cell mass of the animals before going to space and then measured them again when they returned back home. In that case, they would have been matched pairs. But that's not what they did in this study. In this study, they just got two completely separate groups of animals, independent of each other, and they're comparing the two groups. So these are independent samples. So we're not going to run a matched pairs t-test. We're just going to run a two-sample t-test. Okay. I think I've got three more. Yeah, three more. Okay, three more. Part G. The data in the table represent the number of corn plants in randomly sampled rows for various types of plot. We've got the sledge plot, spring disc, no-till. Test whether the mean number of plants for each plot type are different. Well, there it is. Blatantly, we're testing means. How many means? Well, we've got three different types of plot, so we're testing three means. What test do we run? We run an ANOVA, right? We run an ANOVA when we're testing three means. The null hypothesis is that the average number of corn plants is the same on each of the three plot types, and the alternative is that at least one mean is different. Okay, we're going to run an ANOVA test. Easy. Okay, part H. It is a well-known fact, of course, that 24% of children like unicorn giggles very much, 15% of children like them somewhat, and 61% of children like them not at all. A researcher wanted to know if that distribution has changed in recent years, so she conducted a survey asking children, how much do you like unicorn giggles? Very much, somewhat, or not at all? Her results are summarized in the table below. Have children's opinions about unicorn giggles changed since 1994? Now here, we're looking at percentages. They're given to us in the statement of the problem. It seems very clear, right, that we're looking at percentages, so we're going to be testing proportions. Now, the question is, how many proportions are we testing? And I'm looking at three percentages, 24%, 15%, 61%. So it seems like I'm going to be testing three proportions. I've got three categories, right? Category 1, Category 2, Category 3, very much, somewhat, not at all. And so I'm testing three proportions. So now I have to ask myself, okay, I'm testing more than two proportions. Should I be running a goodness of fit, or should I be running a test for homogeneity? We run the goodness of fit whenever we know exactly what the proportions are supposed to be in our null hypothesis. In this case, we want to know if the distribution has changed since 1994. Well, actually, the problem didn't say. I think I edited this and I forgot to change the question, but still, the question remains: like, have children's opinions about unicorns giggles changed? So I'll have to correct that. So not since 1994, just have their opinions changed. This was the status quo, right? And this is what we've collected now, and we want to know if there's a difference, right? Well, the null hypothesis is going to be no, there's no difference. The proportions today are the same as they were here, right? They're the same as the status quo. So we'll be running a goodness of fit here because we know exactly what the status quo was, right? The null hypothesis is that the first proportion should still be 24%, just like it was before. The second one should be 15%, and that the third one should be 61%. The alternative is that at least one proportion is different than stated in the null hypothesis. Okay, and this is a goodness of fit test. So we will be running a goodness of fit. Now we can contrast that in part I here, right? It says a survey was conducted asking children, do you like unicorn giggles? Their responses are summarized in the table. And it looks like it's broken down by their ages, right? So we have different age categories this time, and whether or not they like or don't like the unicorn giggles, okay? Does the sample evidence indicate a difference in the proportion of children in each age group who like unicorn giggles? Okay. This time we weren't given any kind of status quo. We don't know what the proportions used to be. We don't know what the distribution used to be like. We just want to know if the proportion of 3 to 4-year-olds who like unicorn giggles is the same as the proportion of 5 to 6-year-old who like unicorn giggles, or if maybe it's different. And simultaneously, we'd like to test if it's the same as the proportion of 7 to 8-year-olds and the proportion of 9 to 10-year-olds who like unicorn giggles. The null hypothesis would be that, yeah, age has no relationship to whether or not you like unicorn giggles. The proportions in these four groups are all going to be the same, right? That's the null hypothesis. P1 is the same as P2, is the same as P3, is the same as P4. The alternative is that at least one proportion is different. Right? And in this case, we mean different, like different from the others. So this one would be a homogeneity test, right? This is a homogeneity of proportions test. Okay. And that will do it. That will do it for a review of all of the hypothesis tests that we've talked about. You'll have a practice test so that you can practice not just setting up these tests, but also actually running the tests, analyzing the results, maybe computing some confidence intervals and interpreting those, right? So don't think that this is all there is to test 3. I do expect you to actually run these tests, but it would have taken us a very long time to do a bunch of those kinds of examples if we were going to actually run the full thing. So I'm satisfied just setting them up and making sure that everyone's comfortable getting started and getting started setting up the correct test. But that'll be it. And that's it for the course. You have made it to the end. Again, congratulations. And it's been a pleasure guiding you through the course. And I hope that you're able to take this information and kind of make better sense of the world and make good decisions. And I wish you all the best in all of your future endeavors.